So I'm going to talk about what I'll loosely call owl theory tools for mineral physics. And this is a term, at least, that was used in kind of the community where I did my thesis, and I think is maybe a useful framework for thinking about some of these multi-component systems that we've heard a little bit about and might be a focus for some tools we could develop also as a community, or at least integrate some tools that exist out there. Let me just start by acknowledging people who I've collaborated with on this work and financial support, primarily from NSF. And almost everything I'll show you was actually done by Amy Bengston back there. So if you don't like it, you can talk to her. And that's the group who keeps everything running. So quickly, I'll talk a little bit about the stuff I've been doing, our group has been doing, just to give you an idea of where I'm coming from, and then talk about sort of some of these broader tools that I think might fit into our infrastructure needs. I'm going to talk about spin transitions. That's really where my work is focused. I think we've heard a little bit about this, that basically iron under high pressures in these different oxide phases can undergo transitions of spin to different spin states. And our sort of interest was, and this is kind of the alloy focus of the work that I do, is how composition and then coupling to everything else might affect these spin transitions. So we've looked at aspects of this spin transition in ferropericlase, where you sit on a octahedral site in perovskite, where you can conceivably put iron on both an octahedral site, or maybe I should say, sorry, an 8 to 12-fold coordinated site, or an octahedral site, and then post-perovskite, where it can also sit on the sort of 8-fold or octahedral site. So different kinds of sites your iron might end up on. And then we were interested in these different types of structures, and as a function of composition, how the sort of spin behavior evolved and changed. Here's kind of a sort of key result of the type of work we've been doing. We looked at, as a function of iron content, what the calculated spin transition or crossover pressure was in ferropericlase and perovskite. And other people have done some work on this. Renata as well has shown some very nice results that are, I think, in generally very good agreement with what we found. That you get this interesting effect where in ferropericlase, because of the constraints of the structure, you get an effect what one might call chemical pressure, where as you add more iron, it effectively expands the system and it requires more and more pressure to drive the spin transition. On the other hand, in perovskite, that effect is completely washed out by structural relaxations. And in fact, your low spin gets dominated more and more easy to form low spin as you add more and more iron, which is related to changes in the octahedral environment and twists in the structure because of its greater structural degrees of freedom. So you have a very strong coupling of composition to the spin transition and a very strong coupling to the structure type you have. We've also looked a little bit at the post-perovskite phase, focusing actually on a very iron-rich, pure iron version of it. This was related to some experimental work, and also because we just knew less about it, so it's a little less clear how to study compositional effects. It goes through a number of transitions, but we focused on the sort of high-pressure post-perovskite structure and found, and I won't go through any of the details, but that it also had a sort of interesting spin behavior, that there are two different sites, as I said back here, and that this site was always high spin in the calculations and this site was always low spin in the calculations. So again, a very strong coupling to the site and local structure for the spin state. We've then done some work trying to understand the reports of intermediate spin. This has been primarily in the perovskite, although a little bit in the post-perovskite system. Here, we basically made use of ideas of trying to simulate Mossbauer spectra, because the very high Mossbauer splitting that was measured experimentally was often associated with an intermediate spin state. And the interesting sort of result of this was, what I'm showing here is quadrupole splittings that are typically found in systems. Here are the ones that have been measured in the perovskite phase, and here are calculated quadrupole splittings for different spin states and valence states of iron. And the interesting thing we found was that the intermediate spin state was way down here. Didn't look anything like the quadrupole splittings you see up here. And intriguingly, there were multiple apparently high spin states with quite different quadrupole splittings. This again is a result that Koichiro and Renata have also found in this system, and I think, in fact, some additional high spin states that have other quadrupole splittings. And that suggests that maybe that's some of what's going on up here with these high quadrupole splittings in this material. As sort of a next step, and kind of consistent with the focus of my interest, which is really trying to understand alloy systems and alloy thermodynamics and phase stability, we've been interested in trying to take these sort of zero temperature energetics I've been talking about and integrate it into phase diagrams and phase stability calculations. This is a plot of a sort of homegrown model for the ferropericlase system. Here's composition, here's depth, and we're on a geotherm, so that's as a function of increasing pressure and temperature. And these are predicted based on ab initio energetics, the sort of phase stability of this system. And this kind of contour plot shows changing spin state. And this two phase lines show that you do predict a significant amount of phase separation in the system with the introduction of possibly an IB8, some people think a B8 phase, over here in the iron-rich part of the system. So this is just an example of the kinds of ways we'd like to build on our ab initio energetics to understand thermodynamic properties. This is still a pretty preliminary phase diagram. We're doing sort of parallel things of trying to integrate the zero temperature energetics from ab initio calculations, not just into thermodynamics, but also into kinetic properties. This is a calculation of the diffusion constant of iron in ferropericlase, including the spin transition effects. And this is, again, on the geotherm as a function of pressure, so we're changing both pressure and temperature here. What you can see is that high spin iron has a relatively flat profile. Low spin iron is dramatically slower, about 4 orders of magnitude. Also, well, has maybe an order of magnitude or 2 of change. And then, of course, you have to build a sort of thermodynamic/kinetic model to deal with the fact that iron isn't really high spin or low spin as you go through the mantle, has a mixed spin state. You actually end up with something reasonably close to the high spin state that gives you pretty good iron mobility. And if you go through some qualitative arguments about mixing in the mantle, both due to convective mechanisms and diffusive mechanisms, you can show that your diffusive timescales with this kind of diffusion constant are certainly fast enough to get you very good mixing, at least within the ferropericlase phase and transport through that phase. So again, that's the kind of area where my work has been focused, trying to build thermodynamic and kinetic models based on these ab initio energetics. So just to summarize that, basically what we're trying to do is kind of link spin state in particular to all the other properties that you have to think about with iron, including diffusion and things, to try and get at different lower mantle properties. And we found some sort of interesting couplings between these different pieces of physics. So let me now kind of step to what I'm sort of thinking about these infrastructure needs, and it kind of comes out of the type of work we've been doing, because if you think about the problem we're facing here is if we want to understand different lower mantle properties, there's a lot of coupled effects here. I can isolate the effect of spin and composition, but then I also really want to include temperature and its coupling to phase stability and its coupling to iron partitioning, and then that becomes an extremely complicated problem, which actually needs a lot of software tools and sort of framework to embed it in order to do it in a convenient way. And this is really what I would call sort of broadly alloy theory. That's at least what the community I came from called it, which is essentially the sort of tools you use to deal with configurational complexity in systems. So the stress is really on the alloy part. And typically for ab initio-based modeling, it kind of has this general form. You calculate formation energies, migration barriers, force constants, lots of zero temperature data. You integrate that sometimes into thermodynamic models for single phases, and then you parameterize behavior as a function of configuration using a technique called the cluster expansion, which is a very general framework for mapping your behavior of kind of complicated multi-component systems onto a tractable model. And then from that, using techniques like Monte Carlo and kinetic Monte Carlo, you can pull out thermodynamic properties like stable phases, free energies. You can also pull out kinetic properties. So just to give you a 2-minute tutorial on how that works, basically the cluster expansion says if you have a lattice, you map the occupation of each site onto a simple spin variable, and you write out a property of interest, typically the energy, as a function of an expansion in products of those spin variables, hence the name cluster expansion. And you can represent now your energetics with these coefficients, these V's, in a relatively simple way. And it can be very convenient now to do calculations with that. It can be quite powerful. Here's an example of looking at phase stability in a perovskite system with a large number of oxygen vacancies which undergo order-disorder transitions as a function of temperature. And I won't go through the details except to give you a feel for what you might have to do. We did about 80 or 90 calculations of different oxygen vacancy orderings. We parameterized about 10 or so different interactions between these oxygens, and here is the picture of the values we got. And then we used Monte Carlo to calculate the different phase transitions you get in the system, and we do reproduce what you see experimentally. We get some somewhat different temperatures because of vibrational effects, I think, that we ignored. But basically, we get orthorhombic and tetragonal phases correctly, and then a cubic phase at high temperature. And also the order of the transition. Is it first order? Is it second order? This is something you can pull out of Monte Carlo simulation quite easily once you've got the cluster expansion fit established. People have done a lot of very interesting work with this. This is a sort of unrelated example, but gives you an idea of how powerful this can be for exploring areas that you don't really know much about. This is a cluster expansion-based phase diagram from Alex Zunger's group for gallium indium nitride. This is basically the phase diagram of gallium and indium disorder with a fixed nitrogen sublattice. This is what the system does, like many semiconductor systems. It separates at really very high temperature. If you form an epitaxial coherent alloy of the same material, in fact, you get an ordered phase diagram. And this can be a reasonably hard experiment to do. But people do begin to see ordering in epitaxial systems of this. And you can get at this thermodynamics by looking at how your energetics changes with ab initio when you force coherency and epitaxy, and then fitting these interactions and doing Monte Carlo to construct these phase diagrams. Some more work that we did. You can also extend this to magnetic systems. In fact, the Heisenberg model can sort of be thought of as a kind of a cluster expansion. This is a ferrihydrite, which is an iron oxyhydroxide, which pretty much always appears as nanoparticles, which has made its magnetism very hard to characterize. We fit a bunch of interactions of the iron magnetic moments interacting with each other and predicted a ferrimagnetic ground state for that system that is quite consistent with what had been seen experimentally, and is at least a proposed now ground state for the magnetic structure of this system. You can also get at kinetics using these techniques. You have to add migration barriers to the things that you expand. But this is an example from work from Anton van der Ven. Again, as a function of composition, this is lithium diffusivity in a lithium cobalt oxide. You can plot your diffusion constant calculated from first principles as a function of composition. You get these dips that are orders of magnitude in size. These are actually associated with the ordering tendency of the lithium and the vacancies in this system. So you can get at physics that can be really quite hard to measure, particularly if you're worrying about stuff in the deep Earth. Okay, so what do we need for this? I think we've heard a lot about much more thorough analysis than I'm showing here about what we need on the ab initio side. So let me kind of skip that and say that I think if you want to make use of these kinds of tools for doing thermodynamic calculations, these alloy theory tools, in particular cluster expansion tools, there's actually some nice codes out there. There's a code called ATAT developed by Axel van der Waal. There's another code called CHASM developed by Anton van der Ven. You have to be a Belgian to even work on this, apparently. And these do a nice job. So these codes exist. I don't think you'd want to redevelop them yourself, although one could certainly work with them to extend to mineral applications. And these are generally publicly available. There's a kinetic Monte Carlo version, which is really only Anton van der Ven's, which I've worked some on with him, which is reasonably flexible, but could certainly use some work to be ready for prime time. What I think is really something that would be very helpful for our community is, in the end, these are powerful but tend to give you part of the problem, part of a phase diagram. They are not a great tool for doing a 7-component system from ab initio. You don't want to do that. You're never going to do that. It's just way too complicated. What you want is to borrow the physics you can get out of this for looking at multi-component systems for key parts of the physics, say configurational effects. And you want to integrate that with standard thermodynamic modeling of alloys, which I refer to, some people call it computational thermodynamics. I refer to it as the CalFAD method. Very quick introduction to that. It is basically the formalism that you use for calculating phase diagrams. Every time you look up a phase diagram, it is almost always calculated with this method. It's essentially an elaborate fitting scheme for parameterizing free energy functions to calculate phase stability. It's also the foundation for calculating kinetic behavior, because you need the thermodynamic driving forces for any kind of kinetic modeling. These tools are well developed and exist. There are commercial codes that are widely used in material science, ThermoCalc, PanDat. There is an effort particular to mineral science from OFM Research, and many here probably know much more about that than I do. So those tools exist. What I think doesn't exist very